Hello everybody. Today in chemistry, we are discussing the duality of light. This is a portion of the material that's covered in section 5.3 of the textbook. The duality of light can also be referred to as the dual nature of light, and essentially what it means is that light can behave like both a particle and a wave, depending on what the circumstances are. So we are going to begin with when light is behaving like a wave. So when light does behave like a wave, we can describe it and quantify it using this equation right here, C equals lambda V. The C stands for the speed of light, and the speed of light is always 3 times 10 to the 8th meters per second. I do believe that they call it C because it's constant. It doesn't matter what color of light you're working with or what type of light on the spectrum. I mean, X-rays, ultraviolet rays, gamma rays, UV rays, red light, blue light, green light, yellow light, every type of light will always move at that value of 3 times 10 to the 8th meters per second. Lambda is the Greek letter that represents wavelength in this equation. Wavelength has to be measured in the units of meters in order for it to match up with the units of meters per second for the speed of light. So if you are given a wavelength that is not in meters, for example, nanometers is a common wavelength unit, centimeters, you must first convert that value into meters before you plug it into the equation. So in this box right here that I'm putting a star next to, I gave you those conversions. We had talked about that in a previous chapter, but in case you've forgotten, 1 meter is the equivalent of 1 times 10 to the 9th nanometers, and 1 meter is the same thing as 100 centimeters. The V in this equation stands for frequency. The units of frequency are hertz, Hz, named after Heinrich Hertz, I believe, the famous physicist who came up with this concept. A hertz is the same thing as 1 over seconds. Sometimes that's even written seconds to the negative first. So any of those are acceptable. All right, just like we did with the density equation, I put this C equals lambda V into a pie chart here. And remember, on the pie chart, you can put your finger over and cover up what it is that you don't know, and the pie chart will tell you what the answer is. So let me try something here for those of you that haven't been in class. Like, let's say that we wanted to know C, so we're going to cover up C. This pie chart then tells me that C is equal to lambda times V because they're side by side. If I didn't know lambda, I'd cover up lambda, and the chart now tells me lambda is C over V, or C divided by V. So in your skeletal notes that were posted to Classroom, I gave you a couple of sample problems. So I am on the back or the second page where it says, calculate the wavelength of the yellow light emitted by a sodium lamp if the frequency of the radiation is 5.09 times 10 to the 14th hertz. So what I recommend is always list what you are given and what you know. So C, lambda, and V are the 3 variables in this problem. We already know that C is equal to 3 times 10 to the 8th meters per second because that's a constant value that will never change. In the problem, they give us the frequency, and frequency, remember, is V. They say that V is 5.09 times 10 to the 14th power hertz. We are supposed to find lambda, which is the wavelength. So if I use my pie chart, put my finger over lambda, the pie chart says that lambda is equal to C over V. So I plug in my values. C is 3 times 10 to the 8th meters per second. V is 5.09 times 10 to the 14th power hertz. Now remember, when you plug this into your calculator, you have to put parentheses around the scientific notation numbers, which both of them are in scientific notation. When I do that, if your calculator is not set up in scientific notation mode, it will give you the value .000000589. Or if your calculator is in scientific mode, it would call that 5.89 times 10 to the -7th. We need a unit label, so we need to go back and consider what this value is. It's lambda, and remember from up here that lambda is wavelength, so my unit label would be meters, and that's my answer. Problem number 2 says, what is the frequency of a red laser that has a wavelength of 676 nanometers? All right, again, C, lambda, and V. C is always 3 times 10 to the 8th meters per second. In this problem, they tell us that the wavelength is 676 nanometers, and we do not know the frequency. All right, I'm going to draw my pie chart again, C, lambda, V. Now, before I even begin with the pie chart, I need to recognize that there's an issue here with my lambda because I cannot use nanometers. So I need to first convert 676 nanometers to meters. Remember, you put the unit you want to lose on the bottom, the unit you want to go to on top. 1 meter is 1 times 10 to the 9th nanometers. So you take 676 divided by 1 times 10 to the 9th, and you should get 6.76 times 10 to the -7th meters. So I'm going to go up here, I'm going to write that 6.76 times 10 to the -7th meters. Now we have to figure out how to find V. So if I cover up V on my pie chart, the pie chart tells me that frequency is equal to the speed of light over the wavelength. So I'm going to take 3 times 10 to the 8th meters per second, and I'm going to divide that by 6.76 times 10 to the -7th. Remember to, again, use parentheses wisely on your calculator so that it doesn't struggle with the order of operations. And I get a value of 4.4 times 10 to the 14th power. We need to think about what my units are because this is frequency. So frequency's units, remember, are hertz. So I'm going to put in HZ there for hertz. Now, if you think back to the very beginning of this video, we said that light can also behave like a particle. Those particles of light are given a special name. They are called photons. Not protons, photons. Photons are the particles of light. So when light is acting like a particle, we have to use a new equation. This equation, whoops, trying to change my color here. This equation is E equals HV. The capital E here stands for energy, and it is measured in the units of joules, capital J. H is called Planck's constant or Planck's constant. It was developed by Max Planck, a famous physicist, and it is always equal to 6.626 times 10 to the -34th joule seconds. The V is the same V that we were using previously, which is frequency, and remember the units of frequency are Hz or 1/seconds. So we can take this equation and put it in a pie chart where E is on the top and HV are on the bottom. And if you continue through your notes, the next problem that you are given is found at the very bottom of page 2. It says, what is the energy of a photon of microwave radiation with a frequency of 3.20 times 10 to the 11th 1/seconds? So we are working with the energy equation this time because they said energy in the problem. So E, H, and V are my variables. H, we always know, is 6.626 times 10 to the -34th joule seconds. The problem says what is the energy, so we don't know the energy. And it does say that the frequency, and remember frequency is V, is equal to 3.20 times 10 to the 11th, 1/seconds. So I take a look at my pie chart or my original equation, and that tells me that energy can be found by taking H times V. So we're going to take 6.626 times 10 to the negative 34th joule seconds times 3.20 times 10 to the 11th, 1/seconds. Use your parentheses wisely. I would highly suggest actually doing this on your calculator as you're watching the video to make sure that you know how to get these answers. The answer that I get is 2.12 times 10 to the negative 22nd power. And the units, because seconds cancel out, are joules, which is the correct unit for energy. Now, if you think about it, that's a really small number, as it should be, because photons don't carry a lot of energy with them. I mean, when you walk outside, it's not like you're just overwhelmed by all of the energy of the photons hitting you. All right, and the last problem, the fourth sample problem from your section 5.3 notes. What is the frequency of a photon whose energy is 1.166 times 10 to the negative 17th joules? So again, we're working with the energy equation. So E, H, and V. H is our constant value, 6.626 times 10 to the negative 34th joule seconds. This time, we are supposed to find the frequency, and we know that the energy is 1.166 times 10 to the negative 17th joules. All right, if you go back up to your pie chart, you cover up V. The pie chart tells me that V is equal to E divided by H. So I'm going to take 1.166 times 10 to the negative 17th joules divided by 6.626 times 10 to the negative 34th joule seconds. We plug that in to our calculator. And we get a value of 1.76 times 10 to the 16th. And your units can either be 1/seconds, or you could say that it's 1.76 times 10 to the 16th hertz, because those are equivalent units. And that is how you deal with light acting as